Digital memory isn't magic. It is a physical trap, a continuous loop designed to catch an electrical signal and hold it indefinitely. Standard combinational logic doesn't work this way. It's purely reactive. Its outputs depend entirely on the inputs it receives right now, with zero capacity to recall what happened a millisecond ago. To build a system that can remember, look at sequential logic. Notice the memory elements alongside the combinational circuit. The defining feature is this return line. The feedback path takes the output and routes it back as input, constantly referencing its own past. In digital engineering, the binary information trapped inside this loop at any given moment defines the sequential circuit state. But you can't just wire an output to an input and hope the data stays stable. Safely trapping a bit requires a highly specialized, rule-bound logic structure known as a latch. Engineering a continuous logic loop is the only way hardware can remember. But tying outputs back to inputs exposes the system to a dangerous mechanical paradox. We start building that memory with a foundational storage component, the set-reset, or SR latch. Looking at this logic diagram, the latch architecture relies on two cross-coupled NOR gates. To initiate the set sequence and store a data bit, we send a 1 into the S terminal. Because of how a NOR gate functions, receiving a 1 immediately forces its Q' output to a 0. That 0 is carried up the cross-coupled feedback line into the top NOR gate. With zeros on both input lines, the top gate outputs a 1 at the primary Q terminal. The latch is officially set. Crucially, if we drop the S input to 0, the output doesn't change. The 1 at Q feeds back to the bottom gate, maintaining the 0 at Q', which maintains the 1 at Q. The bit is stored. Through this cross-coupled feedback, the SR latch achieves true digital memory. It maintains its binary state indefinitely without needing a constant external signal. There is a severe hazard in this design. What happens if the system contradicts itself and commands the latch to both set and reset simultaneously? Let's look at the diagram and force a 1 into both the S and R terminals simultaneously. The logic immediately breaks down. The inputs force both NOR gates to output a 0. This violates the most rigid rule of the latch. Q and Q' are supposed to be strict mathematical opposites. This function table categorizes the contradiction clearly. When S and R are both 1, the circuit enters a forbidden, undefined state. If both input signals drop to 0 instantly, the gates race to switch states. The hardware effectively rolls the dice, settling on unpredictable garbage data. This undefined state represents a physical hardware vulnerability. To guarantee system stability, engineers had to architect a way to eradicate this condition entirely. To safely implement memory at scale, the hardware must physically prevent the set and reset pins from ever receiving a logic 1 simultaneously. The solution is an architectural upgrade called the data latch, or D-latch. This diagram shows how it resolves the conflict. The primary structural change is that the original S and R lines collapse into a single data input path. The critical intervention lies right here. Notice the NOT gate, or inverter, placed explicitly on the lower input path. If we feed a 1 into the D terminal, the top gate receives that 1, while the inverter guarantees the bottom receives a 0. Send a 0 and the inverse occurs. The top gate sees a 0, the bottom sees a 1. Because of this single inverter, the destructive condition where both inputs equal 1 is mechanically impossible. By evolving into the D-latch, engineers neutralized the risk of indeterminate states. They created a foolproof single-input memory cell that stores what it receives. We now have a stable memory cell, but you can't just let billions of these operate independently. Free-flowing inputs would create massive data collisions. They require an orchestrator. Looking back at the D-latch diagram, you'll see a newly introduced control input feeding into the primary gates. This makes the latch level sensitive. It accepts new data only when the control line is held at a high voltage, or logic 1. In modern high-speed processors, leaving that control window open for an entire level duration is far too risky. Signals must be captured in microscopic fractions of a second to prevent timing errors. This introduces the clock pulse timing diagram and edge triggering. Compare the positive level response in diagram A to the positive edge response in B. An edge-triggered circuit ignores inputs until the exact moment the clock transitions from 0 to 1. Restricting memory updates to these instantaneous clock edges blocks cascading errors. It ensures billions of memory cells update precisely together, in perfect, synchronized lockstep. Because this synchronized logic is so critical, engineers don't draw out the individual logic gates every time. They abstract the entire mechanism into a single component, the edge-triggered D flip-flop. This is the universal graphic symbol for the positive edge-triggered D flip-flop. The distinct triangle at the clock input acts as a visual guarantee to engineers that this specific cell safely updates only on the precise clock edge. When you chain these specific flip-flops together side by side, you form the hardware registers that hold the execution data inside modern CPUs. The physical feedback loop of the SR latch proved that holding a bit of memory was possible. The D flip-flop refined that raw loop into the hyperstable, perfectly synchronized architecture that powers every computer on Earth.